bit, it's this business of elimination. Elimination always competes with substitution. You cannot avoid it. Because, let's say you're trying to carry out a substitution, so you have a particular nucleophile, like an iodide ion, that's supposed to replace a halogen leaving group, and the intention is substitution. That nucleophile is also capable of behaving like a base and causing elimination. Now, a single ion can't do both. It's either going, the iodide ion is either going to substitute or it's going to cause an elimination. But the point is that when we run reactions, there are lots of iodide ions that are going to be present, and if some of them go through the substitution path, but some others go through the elimination path, that's bad. The goal of a chemical reaction is always to prepare a single product in as complete a way as possible. You don't want anything else produced. Most times you have no choice. Organic reactions are typically messy, particularly in the laboratory. Nature has better control of these things than we do in the laboratory, but the idea is the same. The reaction is supposed to follow one path. And it's important to recognize why a nucleophile has this other personality. It's because the requirements for being a base and being a nucleophile are not identical but very similar. The main thing is a lot of electrons. You have to be electron rich. If you're a nucleophile trying to substitute at an electron deficient carbon, remember that's the essence of this. You've got an electron rich atom. And remember, there is a particular atom that is going to bond to the electron deficient carbon. So if you take the cyanide ion, for instance, it's the carbon that has the negative charge. Or a hydroxide ion is the oxygen that has the negative charge. We call the whole thing a nucleophile, but it's really just one particular atom that's going to do all the heavy lifting. So that electron-rich atom has to collide in just the right way with that electron-deficient carbon so that the leaving group departs and the substitution occurs. And that can be either through SN2, which is the one step, or SN1, which is the carbocation two-step. But that's substitution. For elimination, a base is going to pull a proton off a carbon, and the ability of the base to pull that proton off the carbon also rests with the electron richness of the atom. So for a hydroxide ion as the nucleophile, you can see that dual behavior. In fact, you used to only think of the hydroxide ion as a base. What's the difference? It's in what it's doing. A base is always trying to grab a proton. That's the fundamental definition of base behavior, pulling a proton from somewhere. Nucleophile, on the other hand, that behavior, nucleophilic behavior, is going after a carbon that's electron deficient. So it's not pulling off a proton, it's trying to bond to another carbon. That's a fundamentally different process. The general requirements are the same. That is, whether you're talking about a nucleophile or a base, there has to be a very electron-rich atom with a non-bonding pair of electrons. But the biggest difference between the two processes is really how hard it is to get the job done. Nucleophilic substitution is much harder than simply pulling a proton off an organic molecule. You know that protons hang off molecules like leaves on a tree. They're not buried, they're usually quite accessible, and there usually are a lot of them. So there's a lot of low-hanging fruit, so to speak, for a hydroxide ion to pull off a proton. But for a hydroxide ion to act as a nucleophile, it has to sneak into a pretty tight space and form a bond to a carbon. So the two differences there and what has to be done lead to this reverse behavior where something that's a very, very good base tends to be a relatively poor nucleophile. There's a reverse pattern there. Good nucleophile, bad base. Good base, bad nucleophile. What's most important to the nucleophile is its reach. How can it get at that carbon? Now, it helps if the nucleophile is physically small, but it actually helps more if it has longer arms. It's really not the nucleus that has to get into that space. It's the bonding orbital that's supposed to reach out. Well, it's non-bonding to begin with, and then it's going to try to grab the carbon and become a bonding orbital to the carbon. So orbital reach is really the most important thing in nucleophilicity. So if you take a fluoride ion, for instance, F minus, and compare that to an iodide ion, which one is a better base, F minus or I minus? F minus. F minus is a stronger base. The fluorine with that negative charge is much less stable than the iodide ion with the same -1 charge. Why?
Because it has more outer shells. It's
Right. It's the iodide ion. The iodine is bigger. So, you know, if you're a huge nucleus with dozens and dozens of electrons, what's one more? If you're a tiny fluoride ion, the percentage of damage by throwing in an extra electron is much higher. Fluoride ion is much less stable than an iodide ion. And that's why a fluoride ion is a better base. Because it wants to get rid of that negative charge desperately, and the easiest thing for it to do is to pick up a proton. HF, for instance, is really not a strong acid. If you look at those two acids, HF and HI, and the simple ionization of those acids, HF to H plus and F minus, HI to H plus and I minus, which one is a stronger acid, HF or HI? One? Might be an unheard. Yes, HI. Because what really controls this equilibrium most is this species right here, which is called the conjugate base. The conjugate base is what's left after the acid gives up the proton. That's what mostly controls whether that equilibrium lies to the right or the left. And a strong acid is simply one with a good equilibrium to the right. So the iodine ion being so stable allows the HI to ionize. HI is in fact the strongest acid that you can get in solution. It's really very, very powerful. Some people mistakenly identify HF as a strong acid because they confuse its corrosive effect with its acidity. Those are two different things. HF is very corrosive to glass, but it's not a strong acid. So the better base tends to be the less stable. The less stable the ion is, the better it is as a base. Now the iodine ion is a better nucleophile because it's bigger and is more, this is something we haven't looked at before. More polarizable. Polarizability refers to the ability of an electron cloud to stretch, to deform itself in response to some outside influence. Like if a positive charge comes next to the electron cloud, it will try to move towards it. A fluoride ion is much less polarizable than an iodide ion. The difference is pretty much analogous to the fluoride ion electron cloud being like a golf ball and the iodide ion being like a big Nerf ball. Small ions tend to be very tight and dense. They're hard, and the electron clouds are really packed in there. The iodide ion has such a large electron cloud that it's polarizable. So if the iodide ion gets even just a little close to that electron deficient carbon, it can reach, the orbital can polarize and bond, start the bonding from a longer distance. The fluoride ion has to get really, really close in order to start overlapping and bonding to that electron deficient carbon. So bigger means better nucleophile and more polarizability. That's the main thing that controls that. Smaller typically means a better base. Now you can't take two things that seem apples and oranges and compare them. But where this comes in is if you look at like HO minus versus HS minus. You know that O and S are in the same family in the periodic table. Sulfur is right underneath oxygen. So sulfur you want to view as just a bigger cousin of oxygen. It has much the same chemistry, but influenced by a slightly larger size. So is the hydroxide ion a stronger or a weaker base than the SH ion? Stronger, because the O minus is less stable than the S minus. The S minus is bigger. But of course, the HS minus is a better nucleophile. So in that sense, where you're looking at nothing but size difference, big size is better for nucleophile behavior. Small size is not. It's better for base behavior and elimination. So you see those trends in your book. Now, the elimination, remember, is
Yes.
so here's 2-bromopropane. And those are the conditions that I specify to make life easier for you, and not in a cheating way, because if you want elimination to occur, you want to stack the deck in favor of that, which would be a strong base. KOH is a strong base. You want a polar solvent. Alk means alcohol, highly polar solvent, not like hexane. And heating favors elimination, because elimination causes the molecule to fall apart into two pieces. You're going to lose HX and you get an alkene. So one molecule goes to two molecules. That's an increase in entropy. And anytime you have that disordering in a reaction, heating favors the disorder. So high temperature favors that process. All right, so this is going to eliminate, and we know from the laboratory that it's a 1-2 elimination of H and Br. Now, there's no choice about the Br. There's only one. So we're going to lose the Br, but now we have to lose a hydrogen as a proton from not the same carbon that the bromine is on. Don't make that mistake. That's not a, that would be a 1-1 elimination, or an alpha elimination. This is a 1-2 or a beta elimination. And these are the ones that are most common. So I can lose an H and a Br as a 1-2 elimination, actually in two different ways. Because there are different hydrogens on either side of that bromine. So there are two products that would actually result. In an elimination of an alkyl halide, if there's more than one alkene that could be formed, they will all be formed. And you should write them all. So let's say this is the A path, this is the B path for elimination. And I don't care whether it's E2 or E1. I'll get back to that in a moment. But whether it's E2 or E1 is always irrelevant in elimination. It's not always irrelevant whether it's SN2 substitution or SN1, but it is, with elimination, irrelevant. So the A path would be this. In both cases, losing HBr, the reaction is not balanced, but I never do that anyway. And the reaction, by the way, is not stereospecific. So this could actually be cis or trans, or a mixture of both. And it typically does somewhat uncontrollably form both the cis and the trans alkene. But you don't really need to indicate that. It's not a controllable part of this reaction. The main thing is I get two different constitutional isomers, 2 butene and 1 butene. If you run a lot of these, you would find a pattern. And the pattern reveals that while this is not going to give you a single alkene product, which is very unfortunate, it is, however, not a total failure in that it does give more of one alkene over another in a predictable way. And notice I've labeled major and minor. That's the way chemists indicate this is a failure, but not a total failure. I'm going to get a mixture, but the major, the highest amount is going to be this alkene. And so maybe it's salvageable. Maybe with good cleanup skills, I can get rid of the undesired alkene and make this work. Chemists do this all the time. Now, what's the rule? There is a rule called the Zaitsev rule. That covers this reaction. Now, Zaitsev is fortunate enough to be remembered forever in organic chemistry because he ran a bunch of experiments, saw a pattern, and said, this is the rule that will allow you to predict this pattern, and people were kind enough to attach his name to it. Not a big deal, though. It's just an observation. It's not a great theory. Zaitsev rule simply says that in this elimination of an alkyl halide where more than one alkene can result, the major product is the more highly substituted alkene. I have to explain that. The loss of HX from an alkyl halide, the more highly substituted alkene I think the word that he used was predominates. Which is just another way of saying it's the major product that's formed. Now, what do we mean by a more highly substituted alkene? It's simple, but a little bit confusing at first. Alkenes are called alkenes because they have a carbon-carbon double bond. Every carbon-carbon double bond has 4 bonds coming out of the 2 carbons, 2 on one carbon, 2 on the other. So you have an opportunity to put 4 different things on any double bond. A hydrogen is not considered a substituent. And in fact, that's consistent with what you've already learned. Hydrogens are sort of the default condition. But something like a CH3 is a substituent.
Bless you.
In fact, any simple alkene has either hydrogens or alkyl groups attached to it. Hydrogens are just there, the default. But if you have an alkyl group, that's considered a substituent on the double bond. So this carbon-carbon double bond, which is this one here, written in more conventional format, that has 2 substituents on the double bond. What about B? How many substituents are there in the carbon-carbon double bond of B? 1. Now, it happens to be an ethyl group, but it doesn't matter what it is, as long as it's not a hydrogen. So, the more highly substituted alkene is A, 2-butene. So you label that one or expect that one to be the major product. Now, it might be something like 70-30 or 80-20 or 60-40, but better than 50-50 and in this direction. That's the so-called Zaitsev rule. And it only applies to this reaction. It does not apply anywhere else. Now, every observation like this is useful, but scientists, of course, look at this and say, what's going on here? Yes, I can use the Zaitsev rule, but do I know what it's doing? Okay, yes, I can drive my car, but do I know what's happening when I turn the key? Something's going on there. What's going on here? Well, what's going on is not terribly complicated, and it deals with something that you've seen before. Carbocations. The order of stability for carbocations, remember, is that tertiary carbocations are the best. That's why tertiary halides undergo the SN1 mechanism, which requires a carbocation to form, then secondary, and then primary. All of the carbocations are bad news, but the family has some big differences between them. A tertiary carbocation is different from a secondary in a way that relates to alkenes. Anybody spot that? What about an alkene makes it more stable that's similar to carbocation stability? Not the double bond.
Let's say double bond instead of carbon to carbon.
No, it's simpler than that. As usual, you're overcomplicating it. Let's take, the top carbocation is more stable than the one below it. What's the difference between their structures? Substituents. The top one has 3 non-hydrogen substituents, the second one has only 2, and the primary has only 1 carbon substituent. The stability of carbocations depends on how many carbon groups are attached to the carbocation carbon. The stability of alkenes seems to depend, if you make the assumption that A is a major product because it's more stable. A is more stable than B, and A has more carbon substituents on the double bond carbon. So, what do you think about that? Is there seems to be some familiarity between alkenes and carbocations, particularly at the carbon. What might that be? What's the problem with carbocations? Not stable. Why is a carbocation not stable? Because there's a carbon that doesn't have a filled outer shell and has a formal charge. The 2 bad news things for an atom. So, if more alkyl groups seem to alleviate that problem, the logical conclusion would be that somehow carbon groups are better than hydrogens at alleviating this electron deficiency on the carbocation carbon. So it doesn't take a genius to conclude then that carbon groups are more electron donating towards an electron deficient carbon than hydrogens are. And that should make some sense. Carbon groups are bigger with more electrons all over the place. If you had to pick an atom that would be the stingiest at donating electrons, you'd have to be a fool not to pick the hydrogen. I mean, the hydrogen doesn't have anything to give. It's rock bottom. It doesn't even have a neutron in the nucleus. It's only got those 1 shell electrons that are really rock tied to the nucleus. So a hydrogen is the worst at helping out a neighboring atom that's in trouble. Neighboring atom is that C plus. It needs electrons, and the hydrogen ain't gonna provide it. A carbon group is a better scenario. It's not great, but it's better. And these carbocations are so unstable that even a drop of water makes a big difference. You know, to a person dying of thirst, even a drop of water is a big deal. So it makes a big deal whether you have carbons or hydrogens on a carbocation. Now, alkenes, you would, if you extend your thinking like a good scientist, must intuitively have the same problem as carbocations. If the same medicine has the same beneficial effect, more substituents, then we must have the same disease. Now, that's not an ironclad thing, but it's the way you think as a scientist. You think as simply as possible and as logically as possible. A good model for a good scientist is Sherlock Holmes. Science is really a detective story.